RL typically requires an interactive environment to learn, such as a real-world setting or a heavy simulator. However, training and adapting to an unseen environment in these setups is often computationally expensive and highly data inefficient. WAR models solve this by approximating the environment. If we model state transitions and rewards accurately, we can theoretically train an RL agent entirely inside this imagined world. However, WAR models naturally suffer from a variance. This raises an important question: is RL really possible within a WAR model? And if so, how can we address this variance? To answer this, we studied RL on a WAR model using a dynamic pacman task. Our approach consists of three main steps. First, we created a 700,000 pacman dataset. Second, we trained a WAR model from scratch. And finally, we optimized a policy on this WAR model. Hello everyone, we are Team 4. Today we will present our project titled Variance-Aware Policy Learning in State-Based WAR Models. Let's start with our first step, creating the dataset. Based on the widely known rules of pacman, we implemented our own pacman simulator. We then ran PPO on this simulator to collect a diverse set of transitions. The result is a high-quality, large-scale dataset containing 700,000 transitions. This rich dataset captures various policies and scenarios, providing a solid foundation for training our world model.
Second, using this dataset, we trained our world model from scratch. We experimented with over 10 different architectures, and as you can see, our model gained improvements from each step. We started from a basic state predicting model to a model with an additional reward prediction head. After that, we training with a more scaled data, and ultimately achieved promising results with our scaled model, which is scaled with an 8-block GRU and additional layers. While conventional world models typically use pixel-based states, we choose a one-dimensional state space. Pixel models require heavy convolutional networks that can blur special features. In contrast, our one-dimensional state space directly models grid components, keeping the architecture lightweight and highly precise. Here is the high-level architecture of our model. The state is a one-dimensional pacman map, and the action is the agent's movement. The core of our model is the recurrent unit, which updates the hidden state to predict rewards and future maps. Taking a closer look at the recurrent unit, at each step, the action and current state are encoded. A GRU updates the hidden state, which is then used by simple heads to output the predicted reward and decode the next state representation. Our final model achieved remarkable metrics: a one-step pixel difference of just 0.007 and 100% physical constraint accuracy. Even over a full horizon prediction, the average physical constraint accuracy remained at an impressive 99.8%.
Finally, we trained an RL policy based on the learned world model. We initially tried training a PPO policy based purely on state transitions given by the world model. However, as we can observe in this clip, the resulting vanilla PPO policy struggled and often failed. These results highlight the limitations of the vanilla PPO approach. When evaluated on the ground truth simulator, it achieved a 0% win rate. We hypothesized that this failure was due to the inherent uncertainty and compounding errors of the world model's imaginations. To address this, we developed two variance-aware policy learning methods. By running multiple self-ensemble inferences at each state and computing the sample variance, we can measure how uncertain the world model is about a specific transition. We use the computed variance to control the training process of the PPO agent so that it's more robust to the world model's errors. This slide illustrates an example of two state transitions with differing variance. On the left, a low variance state shows a single prediction. On the right, a high variance state shows conflicting predictions where the ensemble samples disagree on the ghost or pacman positions. The first variance-aware method is variance-aware PPO updates. In this method, we dynamically adjust the learning rate based on the computed variance. For states with low variance, this weight is larger than 1, increasing the step size, and vice versa. The second variance-aware method is adaptive rollout truncation. If the variance exceeds a threshold value, we completely terminate the episode to prevent the policy from learning from unreliable hallucinations. When we apply these variance-aware methods to RL training, the results improve drastically. Compared to the vanilla RL policy on the left, our variance-aware policy on the right successfully navigates the maze and consumes pellets to win the game. The metrics reflect this improvement. The variance-aware policy achieved a win rate of 70% when played on the ground truth simulator. Looking at the detailed metrics, the performance of our variance-aware policy is comparable to the policy trained on the ground truth simulator. We were able to successfully recover the optimal performance without the agent interacting directly with the environment. In conclusion, we have two key findings. First, training a policy based purely on the world model is entirely possible if the world model is good enough. Second, variance-aware policy learning significantly improves policy optimization by making the policy robust to compounding errors of the world model. Thank you for listening.